In this video, I'd like to summarize the basic motion equations that we will be using in this class. Starting with this unit and beyond, there are just a few fundamental equations that describe motion. You've actually already been introduced to a lot of it. Here they are, the first three equations, 1, 2, and 3. And we've already expressed these, and here's the variations associated with them. Actually, it turns out that these three equations are all you need to solve all the problems. But we're going to combine them and analyze them a little bit more so that we can have three additional, what I'm going to call derived equations, that's going to make our lives a lot easier. And you'll be happy about that. One of which we've already alluded to, so I will explicitly express it now. So if we have a velocity time graph, it looks like this. Then the initial velocity, v0, is here. Later on, we have a velocity v at some time t. Now the average velocity is displacement over time, or we could say displacement is average velocity times time. Well, if you consider the dimension of velocity, it's the vertical dimension here, and time is the horizontal. So really what we're talking about is the area of the graph. So the displacement is the area under a velocity time graph. So here I'm showing it explicitly with this green filled in section. That is, the area of that is the displacement that is depicted by this particular graph here. So now what constant or average velocity, which you recognize this is not, this is a changing velocity, what average or constant velocity gives us the same area? So we want this green area, but we want one velocity that's constant throughout the entire interval that'll give us the same area. You've probably already visualized it. Wouldn't you just kind of cut it in half here? And so that's exactly what we're going to do. We're going to split that right there in such a way that we know we're correct if in fact this blue part I just added here, which is not part of the area under the graph, and this now yellow area, which is under the graph, if those two areas are the same, it's kind of like taking this chunk here and flopping it over here, then we've got our correct answer. You can see visually that that's the case. And that is exactly how it works. So the average velocity in this case is v0 plus v divided by 2. And that gives us this value right here, the difference between these two values. The average of those is right there. That is the correct answer. So v0 plus v over 2. And this particular point right here, if you consider where in time this is, you'll recognize that it's at the time midpoint, which is what I mentioned the last part of the first video. So the average velocity over an interval of uniform acceleration, which is what this is, occurs at the time midpoint of that interval. Well, now let's take another look at our velocity graph. Here it is. And redrawing the same plot from v0 to v. Now what is the slope of the line? You know slope is rise over run, so it's going to be delta this value, that's delta v divided by delta t. Oh, we just analyzed what physical quantity that corresponds to, and that is the definition of acceleration. So the slope of a velocity graph is acceleration. Now the area is displacement, as we already analyzed, and it's the difference in two positions, so x minus x0. Now the area under the graph can be divided into two sections. So first of all, this rectangular section here, at a constant v0 over this time, we have a displacement. It would be v0t, so the area of that piece is v0 times t. We're going, so we've risen from 0 up to v0. That is the velocity we're at there. And now we also have this triangular piece that we also have already analyzed. Now the area of this is basically going to be 1/2 of this value times the time. Well, what's this value on the vertical? Well, it's the change in velocity. It's from v0 to v. V minus v0 would be that, but that doesn't really help us for where we're going with this. It's also equal to the slope times the time. So we can call this a times t. That's the magnitude of that quantity expressed with this arrow here. So this area is 1/2 at, 1/2 of this value, times the width, which is the time. So 1/2 at times t. So now we have this derived equation, v average is 1/2 v0 plus v, and our fundamental equation, v is equal to v0 plus at. We're going to combine these two together to get a very useful equation number 5. So we're going all the way from 0 to velocity v. And we do that in a couple different ways. Okay, so v average, I'm basically going to take this equation here and rewrite it. It's 1/2 of v0. So there's v0 plus v, but now v is v0 plus at. So we'll put that in and carry that out. We got v average is v0 plus 1/2 at. But it's also true that average velocity is displacement over time, x minus x0 over t. And what's that? Well, that's the displacement under the graph, x minus x0. Let's do a little algebra. X minus x0 over t, which is the average velocity. That's also going to be this, because that's also average velocity. So there it is. Now let's multiply both sides by t, and we get this. And now let's expand that. v0t plus 1/2 at squared. So that is delta x. X minus 0 is delta x, and that is the area under the graph. Well, let's see if that checks out, so to speak. Well, we have the v0t, which indeed is this uniform rectangular piece. Then the 1/2 at squared is exactly what we have in this triangular piece. So those are the two sections making up the area, and that's delta x. So finally, for this very useful equation that we're going to have, it looks like this. X is equal to x0 plus v0t plus 1/2 at squared, and that is our equation 5. And now we have one more final equation to address and define. Okay, so our last equation to solve, and then we'll have the full complement. We'll have in our arsenal everything we need to solve the complex problems I'll be asking you to do. Well, what we're going to do is combine equations 2 and 4. So equation 2, v average is displacement over time. Equation 4 was the first derived equation of 1/2 v0 plus v, or the average velocity undergoing uniform acceleration. Those two equations, we're going to look at equation 2 and solve this for t. T is equal to d over v average. But v average is this, so let's sub that in. There we have d over v0 plus v over 2. And that's 2d over v plus v0. Now we're going to plug this expression for time into equation 3. Equation 3 came from our fundamental definition of acceleration, delta v over t. So the variation to this equation, recognizing that delta v is v minus v0, we had v is equal to v0 plus at. That just comes from this. But now I'm going to stick in this expression for time. Let's go ahead and do that. So that's v0 plus a t. There's t. All right. Let's do a little more math on that. Subtract v0 from both sides. That's what we get. And now we can multiply both sides by this. Let's go ahead and do that. v0 I'm sorry, v minus v0 times v0 plus v is 2ad. Let's carry that expansion out, and we get v squared plus vv0 minus vv0 minus v0 squared is 2ad. Those inner components cancel out, and we're left with v squared minus v0 squared is 2ad. So our final expression here, which is very useful and eliminates a very important physical quantity called time. If we don't know the time in a given problem, but know a lot of other stuff. There it is. V squared is equal to v0 squared plus 2ad. Recognizing that the d in this expression is really the change in position. So you could think of it that way as well. Keep it in mind, now that we have these 6 expressions, that equations 4, 5, and 6 are valid only for a certain kind of motion because they are derived based on the assumption of constant acceleration. And even though that may seem like a severe limitation, I suppose you could say it is, it's extremely practical. When you drop a ball from the ceiling, for instance, that undergoes uniform acceleration. Uniform acceleration is very common in nature. And so these are really very useful for a lot of the problem types that we will be solving. So there you go. You got that in your arsenal. You should memorize all 6 of these equations and be able to use them in the near future. You'll be using them right away. Let's try and commit them to memory as fast as possible. See you next time.